So welcome back everybody for the afternoon session. I welcome our first speaker. It's Weiyong from the University of Oregon. I apologize for any mispronunciation. And the title is Harmonic and Biharmonic Almost Complex Structures. So please, we're ready to follow your talk.
Yeah, okay. Thank you very much. And I really appreciate for the organizers for invitation and to make this nice workshop happening during this difficult time. The only pity is that I cannot go to the Montreal, that beautiful city this time. So hopefully, since we're getting better in near future and we'll have a chance to visit Montreal. So I will talk about harmonic and biharmonic almost complex structures. This is kind of an attempt that I recent years try to study the almost complex manifolds and geometry in general using some modern tools from geometric analysis. So the topics here is about somehow parallel to harmonic maps for people who are familiar with the business. So the outline will be give a short introduction, and then we will talk about energy minimizing harmonic almost complex structures and also biharmonic almost complex structures. So this story dates back in 1990s for almost complex structure. So given a compact almost complex manifold with Riemannian metric, we talk about almost complex structures compatible with this metric. So this is almost complex structure. The compatibility condition is an algebraic condition that it's basically says J is orthogonal with respect to G. So the energy function is just this L2 norm of gradient J. And this functional was studied in 1990s by Chris Wood. Apparently as a parallel story to harmonic maps, so or harmonic functions in general. So this is delivery energy. So the restriction of this almost complex structure, this J square equal negative identity, gives this Euler-Lagrange equation J Laplace J has to be commutative in this way. So it's not instead of a harmonic at Laplace J equals 0, is this condition gives that it's commutative. So a little bit surprising that even though this object was studied in more than now 30 years, it's only this equivalent condition was not even in literature. That's a little bit strange. So when I tried to study some almost complex structure, I realized somehow maybe it's interesting to study this harmonic almost complex structure a little more in a little bit more depth, and then I found this the similarity between this and harmonic maps. It's in particular from this equation. Okay. So this page is about a very rough comparison of harmonic maps and the almost complex structures. I will use this ACAs for short. So they basically have almost the same structure system. And in particular, if we assume the vector metric flat, and for example, in 4 dimension, then since almost complex structure is basically just a section from this twist bundle, when the background metric is flat or conformally flat, then this twist bundle is really just S2 triple bundle on this manifold. So the harmonic almost complex structure in that setting is really just the harmonic maps from R4 to S2 or T4 to S2. So, and in general, there is a technical difference. So this equation is about tensors or matrix, but the harmonic map is about vector valued functions. So they have a quite a big technical difference because this matrix multiplication is not a commutative. So that will pose some hard technical differences. And the geometric difference is this. So at least for me, so this zero energy in harmonic maps. So basically the gradient U is zero, so that will be constant map. On the other hand, for harmonic almost complex structure, this zero energy corresponds to gradient J equals zero. So that's a highly non-trivial condition because that enforced the metric to be Kähler and this GJ to be Kähler. So this difference, this zero energy difference, I think that's the most essential difference between this vector valued version and the tensor valued version. So of course, the motivation then to consider this harmonic almost complex structure basically is try to understand this as a somehow generalization of a Kähler structure. But it turns out these examples of harmonic almost complex structure is much broader than Kähler. So it's quite flexible. So Kähler structure is a harmonic almost complex structure with zero energy. So this very early result is the standard nearly Kähler structure on S6 with the round metric. It's also almost complex harmonic. And actually it's the energy minimizing by some later results that in the subject. I forget who proved this precisely. It's quite a long time in the literature, sorry for that. And some other, in dimension 4, this example here basically says this kind of objects are quite, it's quite flexible. So if you have any anti-self dual metric, which is either Hermitian or almost Kähler, then this will be all actually energy minimizing harmonic almost complex structures. Since the anti-self dual metric in dimension 4 can be glued, constructed by glued construction by the famous result of top. So this is quite flexible condition in somehow. So compared with the very rigid Kähler structure. So we are trying to understand this kind of objects from point of view analytically. So we need to enlarge the consideration. So we talk about this W12 almost complex structure. So solid spaces in particular. So we understand this as a W12 section of the anamorphism from the tangent bundle. So then the countability condition that holds almost everywhere. So it's a measurable one. So almost everywhere point-wise. This point of view is kind of standard in harmonic map theory. The trouble here is, even though this solid spaces uses a little bit information from a differential structure, but since they are not continuous in general, so they will lose a lot of properties of almost complex structure, the smooth almost complex structure. The essential one is this homotopy class, and that will lose. For example, the standard complex structure on the Euclidean space, you can just consider this Euclidean space is together the infinite point as a sphere. Then one would find, of course, then this complex structure will not be well defined on every point of the sphere, but it is a W1P almost complex structure for P less than the dimension of the sphere. So in other words, this solid space of weak almost complex structures, or that's parallel to the solid space of maps between manifolds, it greatly enlarged the objects to consider. So another, if for people who are familiar with the theory of harmonic maps, another consideration is, another reason is, these solid maps or solid spaces or weaker almost complex structures, smooth ones is not complete in this W12 setting. So that's a kind of a very hard problem. And so one question is, people might be studying the completion of this W12 norm of smooth objects in this W12 setting. So the space will be it will be much smaller than this whole W12 setting. But as in the theory of harmonic maps, the technicality seems to be extremely doubting, and very few results in that direction is explored. I think it may be a very interesting direction for this kind of things, the objects. So now we will state some results we got in this direction. First of all, the existence is almost the standard practice of calculus of variations, since you just take energy minimizing ones, and since this W12 is complete, so you will get an energy minimizer. Just like the harmonic maps. The only thing that harmonic maps in the convex setting is the energy minimizer is always 0. So it's always constant map. So that's trivial. But in our setting, we cannot get that. So we get energy minimizer. So the other one is the regularity. So in general, this kind of objects have singularities, of course. But this is a semi-linear system. So essentially, it's like a Laplace u equal gradient u squared, so quadratic growth on the other side. This type of regularity, if we know that this guy is continuous, then one knows that it's actually smooth. Actually, this continuous, even one can say that locally, if their oscillation is very small, then that's enough. Do not even need continuity. So the trouble is this J compatibility condition tells us J is W12 and pointwisely bounded, but locally it can be still an infinite function with very large oscillation. So that will cause the singularities. Any questions so far? So that's this part.
Weiyong, can I ask a question?
Yeah, sure.
Yeah, so along a minimizing sequence, is there any bubbling, or along the flow or the minimizing sequence, is there any bubbling? Because you say there is always W12 energy minimizing.
Here, there's no bubbling coming from. So because we do not restrict any homotopy class or whatever, so that's no bubbling. So you just converge to an energy minimizing one.
I see.
When we talk about this biharmonic ones, so that there will be standard bubbling phenomena happen.
I see.
Okay. So this comparable result in harmonic theory is trivial because this energy minimizer is just constant map, 0 energy. But in our setting, this will be somehow, it should be interesting, but yeah. So the second one will be to study the energy minimizing harmonic.
Weiyong, I'd like to make, this is Weiyong, this is Claude.
Yeah.
I'd just like to make a comment. You mentioned almost Taylor anti-self-dual four manifolds.
Yeah.
And you were sort of saying, well, you can easily cook up anti-self-dual four manifolds by gluing, but usually they're not almost Taylor. Actually, yes. This is an extremely delicate issue, and there are papers on this. It's in particular.
Yes, excellent. So I'm saying it's just it's compared with the Taylor, it's rather flexible, but yeah. So thanks.
So it's an open condition in the moduli space of almost Taylor of any self-dual metrics. If you have such a thing which is almost Taylor, then you can find other almost Taylors near it. Right? But it's typically in most anti-self-dual four manifolds are not almost Taylor. Even it's a conformal after conformal change even.
Okay. Most can they be Hermitian in general?
No, they're very strong conditions.
So in general, that's yeah. Once
it turns out that there was a lot of work by Charles Boyer on that in the mid 1980s, and so I mean it sort of largely reduces to the question of scalar flat Taylor manifolds. When B1 is even and when B1 is odd, then there are some very special So I constructed a lot.
Yes, thank you very much. So
There's certain
haven't-
surfaces in class 7, yeah, but it's rare.
okay.
The topology is severely restricted.
So now we're trying to talk about the energy minimizing harmonic almost complex structures, this regularity series. So basically the statement here is purely parallel to the theory in harmonic maps. So the first one is this partial regularity, saying that if we have a small energy, this scaling invariant small energy in a ball, so this ball is some fixed ball, since this metric is fixed in this setting. So this ball you can either take as a geodesic ball or Euclidean ball, which are small enough so that this ball will be equivalent to a Euclidean one. And if this scaling invariant energy less than epsilon, so this epsilon depends only on the background geometry, then this is smooth in let's say definitely smaller ball, the 1/4 ball, and then one can get all higher derivative estimate in terms of this this formula here. So the singular set for the energy minimizing, it has a dimension at most n-3. So in dimension 4 in particular, so the singular set will be just one dimension at most. So, but I think one cannot really improve this because there are examples, lots of examples of this type. And we have some examples also. So one can be more precise about this singular set. So they have a quantitative stratification due to the consideration of the singularities at the tangent cone at the singularities. So once using this theory of quantitative stratification, one can improve this a little bit of the energy bound. So one can push to this almost L3 or yeah, so L3 gradient J is almost L3. This 3 is the optimum. So the first part is parallel results of the Schoen and Grunberg in 1980s. The late part 2 is the results, corresponding results of Aaron Neighbor and Jeff Chicker, I think. Yeah. So that's the corresponding results. We can mention a little bit about the strategy of the proofs. So both proofs are very technical and quite hard and very long. So when I try to understand this, I spent a very long time to study their papers to understand all the technicalities. And then eventually I found that there is no essential new technicalities, that's no essential difficult technicalities beyond their paper. It just need to be modified to adapt with this new setting. So the essential thing here is the structure equation is just the same, as it's essentially the same tensor valued version. And then the strategy works for the harmonic map. But there is one new difficulty. It turns out it can be overcome using a matrix decomposition, quite canonical one. So this one essential step is about the monotonicity formula. We will mention a little bit details for people who are not very familiar with the harmonic map theory. So to get monotonicity formula, one needs to construct some comparison maps or comparison almost complex structures. The method in Schoen and Wollenbeck is constructing something like this. So in a small ball, and then replace this by this one, is in the radial direction, just extend directly from the ball, yeah, this x equal r ball directly to the center. And then when x equals 0, this is not well defined, but it's still in W12. So that's all okay. And once one have this comparison, almost complex structure, and plug in the energy minimizing condition, one will get a monotonicity formula. So the trouble here is this comparable, almost complex structure is not compatible with the metric G background one because you change the points. So we need to somehow modify this construction. So that's the really new difficulty, and also the adaptation of the method to this almost complex structure setting. So a little bit details from this harmonic map theory. Even though I write this 3 points very short, the actual technicality in the 82 paper is quite involved. It's very dedicated. In particular, this part 3, this decay estimate. So the key towards this partial regularity is the decay estimate, based on the monotonic formula, this one. So consider here, because this is a semi-linear system and the background metric is not is fixed. So all the statements and methods to prove is essentially local. So we can just fix a ball on the manifolds. So we can assume that G is almost Euclidean in this Euclidean ball. So we use this very roughly speaking, we just measure the difference of this G to the Euclidean metric in this ball by a small constant delta and fix that. So we consider the energy in this small ball. So when R less or equal than 1, so this monotonicity formula basically says the scaling invariant energy essentially it's monotone when R is increasing. So this delta just measures the difference of this G to the Euclidean metric. When delta is 0, then you will get a strictly monotonicity formula. Once one have this monotonicity formula, then one can prove that if in this ball, this energy is sufficient small because the radius is 1. So you just need 1. So the energy is sufficient small, then there will exist a constant such that this rescaling invariant energy at this radius is less or equal than half. So this number is less than 1, and that's sufficient enough. And once this decay estimate is established, one can use rather standard theory in this setting to prove that J is actually Holder continuous. So once the Holder continuity is established, then use the structure equation, one can just prove smooth. So monotonicity formula together with this decay estimate, I think that's not work in general for a structure equation with similar ones, but a higher order estimates works for very general semi-linear systems. So for this part, that's and the other part about this, so this part 2 and 3 is basically just the direct adaptation of this trig and neighbors regularity result. It's extremely complicated technically, so I'm not going to explain that. I have learned this several years ago, kind of the memory of, of this technicality is going to fade off a little bit already. So, and I will explain a little bit about this almost monotonous formula, how one get that. So in this series, the regularity series, this one is quite different compared with, for example, the elliptic equations that a priori estimate for this very nice nonlinear equations, usually equivalent or with some effort equivalent to regularity theory. But in these elliptic systems, the a priori estimate and the regularity are greatly different. So if it's sufficient smooth, actually, if that's the I think it's sufficient smooth. It's very easy to compute use the equation that this quantity is monotone. Here we chose delta equals 0 for simplicity. But if the metric is not Euclidean, one just need to modify a little bit. So this follows from the structure equation. But we do not know any smoothness beyond the W12 at the point. So to get a regularity, one need to establish the monotonicity first. So one cannot make sense of this quantity, the derivative. That's the key part. And in the harmonic map setting, if one just assume that the equation holds weakly, I think a famous result by Revere constructor when the dimension is n bigger than 4, that the weak harmonic map does not get any regularity. So every point is not smooth. Every point is singular. So that's a famous result in this from 80s. So then Schoen and Wollenbeck's idea is for W12 energy minimizers, one just consider a comparable map like this in the R ball, and then outside R is a fixed number, let's say less or equal than 1. Then just apply energy minimizing condition that this one less or equal than the comparable one. And this condition essentially just gives you this one. That's essentially equivalent that will get this condition somehow. So, but in our setting, since that's a almost complex structure, is not compatible with the metric. So one need to modify this setting. So we need a canonical construction. So basically, it's a pointwise decomposition of a matrix. Suppose we understand this. In this case, we take just the metric to be identity matrix at a point. Then given a almost complex structure that's just a matrix with square equal negative identity, then we decompose this matrix by the symmetric and the antisymmetric part. Then use n square equal negative identity, we will find the antisymmetric part and the symmetric part will be skew commutative. So the sum will be 0 here. And then negative a square equals identity plus s square. So that's a symmetric positive definite matrix. So one can take square root, then take square root, and then we construct this. Not the standard construction will be square root of this guy, then is skew symmetric, and then square is -1. So by skew symmetric in this case, that means that is compatible with the identity matrix or compatible with the metric. So with this construction, we need to decompose this JR into a compatible, almost complex structure with G, with the background metric. And then the point is, since in this small ball, the metrics are very, very close to each other. At every point, it's close to identity. So this decomposition will not default JR by that much. So that will imply the almost monotonous formula. And then with this, then together with the adaptation of Schoen and Wollenbeck's technique, we can establish this partial regularity. So that's essentially the story. Okay. So as I mentioned, maybe since for this smooth setting, almost complex structure, we have for this homotopy classes and then the invariants essentially from, for example, the Chen classes. And then in this setting, all this information will be lost, W12 setting, that since in general, they are not continuous. In particular, in S4, we can even find such a thing. And an interesting phenomena is in S6, both this standard complex structure in R6 and the nearly Kähler structure, they are both energy minimizer, absolute energy minimizer. So that's kind of mysterious for me, and since by the structures that I do not fully understand this phenomena. And For the partial regularity, I do not think one can push further, like say get better ones than this codimension 3 singularity. So one thing to consider this smooth setting is to enlarge the derivatives. So we consider this one in 4 dimension. So we are trying to study the actual almost complex structures. But this kind of is studied in harmonic map theory also, so called polyharmonic maps or biharmonic maps that we consider in 4 dimension in particular, even though most of the consideration will hold for even dimensions. And then this bi-energy here, we consider Laplace J square. And the requirement then J becomes W22. So even though it's not W22 in dimension 4, it's still a critical dimension. It's not quite enough to embed in the continuous one or even L infinity one. But it turns out that if we have W22 maps or W22 almost complex structures by a very nice result of Brown White in 90s, he studied the solving maps, that this homotopy classes of maps, or we can say homotopy classes of these almost complex structures make sense for W22 setting in M4. So one can prove that essentially just if this manifold support a W22 almost complex structure, that it will support a genuine or smooth almost complex structure. So we will talk about the critical point of this energy function in 4 dimension, and that's just double Laplacian J is commutative with J. And using this J square equal-negative identity, one can apply that to get a 4th order elliptic system with this right-hand side Q0. But this Q0 is quite involved, very long, because double Laplacian operator here. We will skip these details, and this equation looks much better, the top one. So using integration by parts, so we will talk about a weak solution satisfies this equation here. That's the integration by parts. So it makes sense for W22 almost complex structures. So now here we will talk about a little bit about
the test section. You never gave it a name, but then it's in the equation, right? Okay. Any section K of the endomorphisms.
Yeah, any test section K. Sorry, so that should be this one. Yeah. So that's does not have to be in the 10. So it does not have to be commutative with J. Yeah, any test section of this endomorphism would be good. This one. And then we will talk about the existence and regularity. So again, existence is a standard practice of this calculus evaluations. And the interesting part is this kind of objects regularity is always smooth. So that's the difference when we enlarge or when we increase the derivative. So, but even though somehow the regularity is, we should just say it's standard in the subject now, but actually the actual proof is very hard. So I will go through this regularity theory a little bit, and for people who are not familiar with the theory of harmonic maps. So the starting point is Helen's very nice result in 1990s to prove that the W12 solution of the elliptic system of harmonic maps from surface, from a surface that's a critical dimension, is always smooth. So this is basically saying that he did not need any additional assumption, just a weak solution will be smooth. So that's somehow very surprising, because this certainly does not work for a general elliptic system with similar structure equation. So his method is in particular tricky, but explore the special structure of this right-hand side of the harmonic maps. And in this direction, it has a great development. And since I'm not an expert in this afterwards, or I will skip to discuss the details of this in this development. So I will only mention the things that are closely related to what we are going to use. So in 2000s, at Zhang, Wang, and Yang, they proved that W22 biharmonic maps from M4, a general target, into spheres are always smooth. So their proof is different from Helen's, and but they still use the fact that this right-hand side have a very special structure. They call it a generalized like a divergence form. So this was generalized to all target manifolds and for all K polyharmonic maps in critical dimension by Wang and Gaston and Schwinn. This, I think, in 2004, this is 2009. So for us, then, our equation is actually tensor valued version of this, this biharmonic maps into sphere. So we found that their structure equation, their structure particularly interestingly applied to our setting, even though the proof is quite different and it's much more involved because of tensor valued, basically because the matrix multiplication is not commutative. So we found that we have the similar structure equation as Zhang Wang Yang's paper. And then we will have to use the method or language somehow like a Lorentz spaces, very special structures like this to prove that. And then we prove this W22 biharmonic almost complex structure in dimension 4. It's always smooth. And in dimension 6, then we can prove this W32, 3 polyharmonic almost complex structures. It's also smooth. In general, I believe this polyharmonic almost complex structure certainly is smooth in any dimension, but because of the technical difficulty that we do not find a nice way to say that this kind of objects actually satisfy a very special structure. We prove it using brute force to do this computation, and it happened that just M4 is manageable, M6 is quite complicated, and but still manageable. And beyond that, after some try, we gave up. So it's kind of this is very technical things, and even though that's kind of well understood by the specialists in the subject. So interesting thing in this is, since this W22 objects are actually smooth, so we can talk about then the actual topology and the geometry of this almost complex structure. So we can fix homotopy classes. So basically the talk up to now is just apply the existence theory in the harmonic map and polyharmonic map or biharmonic maps to this new setting. So there's no essential new input, just adaptation. So the existence, when we consider a fixed homotopy class, actually contains some new developments. So we are going to summarize. First of all, we can talk about this energy minimizing case with a homotopy class of an almost complex structure fixed. So this homotopy class of an almost complex structure turns out to be quite a delicate topological things. Since I do not understand it very well, so I will assume this 4-dimension is simply connected. So that it will simplify the discussion a lot. Then the homotopy class of an almost complex structure is essentially determined by the first Chen class, and also with the spin structure. So that's the delicate part that I do not really understand. And to make things worse, that there are contradicting results from the specialists and the top experts in the subject in this thing. So, so we will see. So given the first term class, one can construct two, I should not say two homotopy classes. So I do not know precisely what's happening here because there are contradicting statements in literature, even though it will not affect our results at all, but I will mention this. So one is, if M is non-spin, then this first term class will uniquely determine homotopy classes. And if M is spin, there exists exactly the two homotopy classes. We know that there are at most two. That's I know for sure. But whether when this M is spin or non-spin, there is a unique one that I'm not sure, because in the literature, there are two answers from top experts that I also asked many experts. I do not get a definite answer. So we will see why this is happening. So this is related to the fact that this pi4 of S2 is Z mod Z2. So because the almost complex structure is the twist bundle, is a section of a twist bundle on M4, so the fibers is actually S2. So that's why this guy is coming into the play. And Dawson in 1990s construct this operation on K3 surface. So K3 surface in particular is spin, so there will be exactly two homotopy classes, as we know, corresponding to a given first term class. So our statement is following. So this M4 is simply connected. It's just a technical assumption. We do not really need that. Once we sort this topological thing out. So given the first term class C1, if M is non-spin, then there will exist energy minimizing biharmonic almost complex structure in each homotopy class corresponding to this first term class. If M is spin, then there exists an energy minimizing biharmonic almost complex structure in at least one homotopy class among these two homotopy classes corresponding to the first term class. Unfortunately, I cannot improve this one to more clear statement. We can only combine these two homotopy class together corresponding to the first term class, and then take energy minimizing sequence to get a result, to get an energy minimizer in these two classes. What I believe is one class will have the energy minimizing one, the other one will not, but I roughly know what might happen, but I'm still working on this, so it's not very clear what's going on here. So technically, it's quite complicated to see clearly what's happening. So that's any questions so far? That's the statement. So this is actually new. There is no parallel things in harmonic or biharmonic setting. The essential thing here is in the elliptic system case, that even though we have a nice a priori estimate or regularity theory, but actual proof, the existence is another issue. So for example, our method and the results can be applied to some existence result of biharmonic maps. That regularity theory was actually known more than a decade, but our result and method can actually be applied to prove the existence. So that's kind of new. And so we'll mention a little bit about what's happening when the assumption on this simply connected one is dropped. So we will go through a little bit about this Donaldson's operation to see why this topology comes into the play. So Donaldson construct this operation on homotopy classes of a complex, of almost complex structure. So he construct is just this structure is the square is identity, and it preserves the C1. So in the end, this is very geometric. So in the end, when there is a time, I might describe use a picture of what's happening. So essentially what he did is just take a small ball and on this manifold, and then replace this small ball, the fibers, this small ball, the almost complex structure, the homotopy class will differ by a non-trivial element of this Z2 in this group pi for S2. So since this operation is happening in locally in a ball, and this first chunk class is just the information from two skeleton, since it's H2. So certainly it will not change the first chunk class. And then since this Z2 is only two elements, so this P square equal identity. So the only thing that I did not know is whether P itself is identity or not on this almost complex, on this homotopy class. So they are two contradicting somehow the statements. One is this two, this P, and let's say this P is never identity. The other one is this P is identity when M is non-spin. So I tend to believe that's what's happening when M is non-spin, then this P is actually identity. I do not know proof. Let's put this way. So the Professor P. Teichner posed a proof on mass overflow that I found seems, from my point of view, I seems to be understand that, but I checked with him, sent an email, and I did not get feedback. So that's unfortunate. Anyway, so I tend to believe that P is identity when this M is non-spin, so that corresponding to this one. So nevertheless, if this is a compact almost Hermitian form manifold, then at least one of the homotopy classes of an almost complex structure, the sigma and P sigma, will contain energy minimizing by harmonic almost complex structures. So in other words, if modular this operation, this Donaldson's operation, we put these two homotopy classes together corresponding to the same first chain class, then we can prove this object, these two homotopy classes will definitely contain energy minimizer. So Peter Teichner's proof about this sigma and P sigma is the same when M is non-spin, is for simply connected case. So I do not know whether this is true or not when this simply connected condition is dropped. So that makes the statement and this kind of thing a little bit messy. But the technicality and our analytical technicality and statement essentially works for all these settings. That's modular this topological thing here.
So when the four manifold is, this is Claude again. When the four manifold is not simply connected, then an almost complex structure determines a spin C structure, which contains more information in a non-simply connected case than just C1. So the issue.
Yes. So there is information from the H3 actually. So yeah.
So no, the extra information that you get so in terms of the distinction between C1 and the spin C structure is that that depends on information having to do with two torsion in the homology ring. So if the fundamental, if H lower 1 has non-trivial two torsion, then it turns out that the first Chern class does not determine the spin C structure. There's still an ambiguity.
Yes, thanks. Unfortunately, I only roughly understand the statements. I do not understand these technical details at all. So, for example, in S1 cross S3, that we know that all Chern classes are vanishing, but there are lots of homotopy classes coming from this H1 of almost complex structure. Actually, almost complex structure is homotopy class is Z, so classified by this H1. So, yeah. So we'll mention a little bit about proof. So the proof is like this, goes like this. So we take an energy minimizing one, so it will converge by subsequence to a limit. So this convergence is weakly. So that's the case that we have a bubbling. So, but the weak limit is still satisfying the equation. So we know that the limit is smooth. So the only thing that we need to prove is try to understand what's going on about the weak limit process. Since you can see that if the convergence is strong, then the homotopy class will not change. But we know definitely homotopy structure might change. And so then what's happening? We need a very clear understanding of what's happening when this strong convergence fails. So the key step then is proof energy concentration lemma. So the failure of a strong convergence in W22 leads to energy concentration around discrete points. So around, in this energy minimizing setting is actually around 1 point. So this step is actually an epsilon regularity for minimizing sequence. So it's much more delicate than the epsilon regularity for harmonic maps. The reason here is because for harmonic maps, one actually have an equation to work on. So even though that's very involved, but here we do not have any equations. So we need to work on minimizing sequence, and the energy is more enough around a point, then the convergence is strongly in W22. So that's the key step. So the proof relies on a local grafting technique in W22. So this result was not known analytically in harmonic setting or biharmonic setting. So the essential point is, I think this comparison technique was already shown in the Uhlenbeck's paper. So they need to use the fact of this grafting. They need to use the fact that Euclidean ball is essentially by Lipschitz equivalent to the cubes. But in our setting is W22, we need to work out somehow like, so we cannot use their technique to prove this grafting technique. So it's very, very involved. So I will not be able to explain the technicality here. So this will combining a delicate choice of cutoff functions and average technique. This average technique is the same as in the paper of Schoen and Uhlenbeck. Essentially, I learned from that paper. And then, so as I mentioned, so this step technically is even new in the setting of harmonic maps and biharmonic maps, I should say. So we can actually apply this one to the existence of biharmonic maps and polyharmonic maps in that setting. And even though the regularity theory was known long time ago. So, and any questions so far?
No, go ahead. We have like 10 minutes.
So I will mention a little bit about the future problems. So why I'm interested in these things. So I believe this is kind of too optimistic, but still I think that having a dream is important. So what I had in mind is this one. So I believe that in 4 dimension for almost complex manifold, it should have a cohomology class. That's essentially differential invariant that depending only on the different structure of this 4 manifold. So let me state this particular problem that I had in mind. So suppose we have a compact, simply connected and non-spin 4 manifold, which supports an almost complex structure. We try to prove that always exists a cohomology class C1, which remains unchanged, corresponding to the first Chen class of absolute energy minimizing biharmonic almost complex structure for a generic metric. So in other words, you can change the metric, and then certainly the absolute energy minimizing one. So now we modular order or the homotopy classes, the absolute energy minimizing biharmonic maps might change, definitely will change, and then certainly might not be unique. So in particular, for example, K3 surfaces, the Kähler structure, the complex structure forms a moduli. So this, but we believe that for generic metric, this energy minimizing biharmonic almost complex structure, their first chain class should remain unchanged because this quantity kind of is kind of an integral quantity, and then this deformation of matrix is smooth. So I hope, or at least I wish, that this will not change. So in particular, when M supports a Kähler structure, then this first chain class should be just the first chain class of the Kähler structure. And this, suppose this statement coincide with some known statement already in the four-dimensional geometry from the Seiberg-Witten series, since I'm not an expert either in that direction, definitely. So I will not discuss the details of this. But I believe this should be true, but I do not know how to prove it. So that's the kind of a big question I have in mind, why I'm interested in this kind of objects. So the other one is the quite technical one. So maybe what's happening when M is spin. So this sigma, these two homotopy classes are not the same than what's happening. So I believe that one homotopy class admits absolute admits energy minimizing biharmonic almost complex structure, while the other one does not. And the energy minimizing sequence in the other one then should jump to the energy minimizer in this class with energy bubble off a non-trivial biharmonic maps from R4 to S2. So even though this, we know that exists by our technique now, but we lack the detailed understanding of this kind of biharmonic map. So I should stop here, and thank you very much.
Very much. We have a first question in this audience.
So the conjecture that you're making in the first statement cannot be true because of the following sort of thing. First of all, given an almost complex structure, J, then minus J is another almost complex structure, and it will have that changes the Chern class by a sign. So C.
Oh yes, the modular sign. Sorry, I should be more careful. Thank you very much. Yes, modular this sign. Yes.
In the Kähler case, you get lots of changes of sign, but also the typical thing is that if you have a non-minimal complex surface, then if you start with a complex surface and then you blow up a point, then actually on the new complex surface, there are more choices of C1 for integrable complex structures of Kähler type. So the thing is that you add an extra generator to H2, and the sign of C1 on that can also be changed. There are self-diffeomorphisms that change that look like complex conjugation on that added C1. So in Seiberg-Witten theory, when you're looking at the so-called basic classes of a four manifold, in the case when it arises as a complex surface, for surfaces of general type, then the classes you get are, well, plus or minus the first Chern class of the minimal model, and then plus or minus you have other signs. If you've blown up k times, you get you get k extra choices of signs. So in fact, they're sort of 2k plus 1 different choices. So that would be the best thing you could possibly hope.
Yeah. So may I ask you later for the details? So yeah, should it be positive or minus? Yes. Thank you for that. Yeah.
So but in addition to that, you can have different C1s with different Kähler metrics on the same smooth manifold, because there are diffeomorphisms of the four manifold that don't preserve C1, and so all of these things are sort of modulo self-diffeomorphisms of the four manifold.
Okay. So may I ask you for the details? Thank you very much. So yeah.
Sure. I can send those to you by email. Or there are many standard references for this.
Okay. Thanks.
I have another question. So you seem to be able to say something about dimension 6 but you need higher regularity. You need I guess W3 rather than W2.
Yes. So basically just just the critical dimension. Then you need to enlarge that increase the derivatives. So only W3 2. So then we call it just 3 harmonic almost complex structures in dimension 6. Yes. So they are always smooth.
So there's a cute thing in dimension 6 in terms of existence of almost complex structures. It's actually much simpler in dimension 6 than in dimension 4. A 6 manifold, a compact 6 manifold admits almost complex structures if and only if it has a spin C structure. And so there's a very simple obstruction that you could check. So
okay, great. Yeah.
Whereas
Thanks.
It's a bit more delicate.
Yeah. Okay. So may I ask you this in detail about this question here? Since I hope if this is not true, then I just don't need to have to spend my time to work on it anymore. That would be great for me too, even though that's maybe not my intention, but that would be great.
Okay. I'm asking to the wide audience out there at the computers. So if there are any questions left, this is the moment for posing them. No. Okay, then thank you very much for the nice talk and coffee break, and see you all after.
Thank you very much.